Hello and welcome back to Real Seekers. I'm your host, Dale, the Real Seeker, and today I have a really great Shroud Wars panel review debate between, whoops, sorry, we're missing one of the debaters. So I am joined by Hugh Farey. So first of all, hey there, Hugh, how are you?
Hello, everybody. Yes, sorry, it's me again.
Yep, the ultimate Shroud skeptic himself, the nefarious guy. But on the other side, for representing the pro Shroud side, we have nobody. So this was originally we were supposed to have Paul Bruney on. I have no idea what happened. Maybe he's having technical issues or something happened. But basically, I received a fan request from Annette Cloutier telling me about Paul Bruney's quantum theory interpretation for how the images formed on the Shroud of Turin. And so I wanted to bring on a panel review show with Paul Bruni, who agreed to be on to discuss with Hugh Farey about his specific quantum hypothesis, so to speak. Unfortunately, as I said, Paul's not here, so hopefully maybe he'll join later on. But in the meantime, me and Hugh will discuss his theory because I think it deserves to be discussed. Um, Now, one thing I'll just say before I go to you, Hugh, I know it looks like you're drawing something, but I just want to make a recommendation I got. This comes from Dr. Mike Lacona, where he recommended a new guy on the Shroud who's a scholar, but he has great presentations. His name is Oliver Sang. Is that showing up there, Hugh?
Sorry, looking in the wrong direction. Yes, CSEN, Perimeter Church Harvesters Class.
Yep. So
Oh,
I'll,
yes.
Mike Lacona, I'm going to be appearing at some point on Mike Lacona's channel with Oliver Sang. And Mike has a lot of respect for Oliver, and I've been watching some of his presentations on the Shred of Train. He does a great job. So yeah, I just wanted to give that recommendation before we got into today's topic.
I've watched a couple of his too, and they're very sensible. They're
Awesome.
wrong, but they're very sensible.
Of course. Yeah, Hugh, before we get into today's topic and looking at quantum physics interpretations of the shroud images, is there anything you want to announce? Anything new on your end? Yeah, you've been having a back and forth with
No, not really.
Lulu. No?
No, no, I'm just carrying on.
Fair enough. Fair enough. Okay. Well, with that said, let's get straight into today's topics. And just before we get into looking at Paul Bruni's quantum tunneling hypothesis for the shroud images, I thought it was very interesting because it related to a paper, conference paper that I went to by a philosopher named Scott Hill, and he has a theory about the resurrection that involves quantum theory and stuff like that. So I'll just show my screen for a second, but um, oops, it's in the way. So Scott Hill, he has the no collapse theory of the resurrection of the dead. And I asked Hugh to go over that paper with us and just describe and evaluate his theory here. So, yeah, Hugh, let me turn straight over to you. In terms of Scott Hill's interpretation, basically, he says that, well, how could we explain the resurrection? Assuming substance dualism is false, there's no such thing as a soul. Jesus had a body, he died, but at that moment, his body went into a state of superposition, quantum superposition. So that means it was both dead and alive. And he thinks that through this understanding of quantum physics, eventually, okay, we can say that he has a resurrected body without positing a need for a soul or anything like that. So, what's your sort of notion on Scott Hill's hypothesis for the resurrection proper?
Um, I think he's likely to confuse. He does confuse a whole bunch of concepts. But let's assume for a moment that I mean, he says that we have sort of two parallel bodies, um, as it were, and when we die, we get a choice of which two to go into. Why would this be? I'd like to know, when we die. Is it because the body that we're in is no longer functioning? But if the parallel body is exactly parallel to it, then that will no longer function either. I don't see why one should die and the other one not. Is there ever a situation when perhaps the 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 consciousness body that we can't normally see, does that die? And then, in case, what happens to the physical body? Perhaps we turn into zombies. However, I've just the reason I drew these little pictures. I hope you can see them.
Yeah.
Is because I want to just. This is only one paragraph, literally almost the first paragraph. It is the first paragraph after the abstract of his paper, and he says, "Let's adopt a metaphor. Imagine two drawings of a chair. Each drawing is on an otherwise transparent sheet. For convenience, I haven't drawn it on a transparent sheet, but imagine we can see through all these drawings, and all the pictures of the chair are on top of each other. Now, in one drawing, forget the third one for the time being, the chair is standing in its normal position, and in the other, the chair is knocked over. Okay, that's fair enough. We call this stack of drawings a superposition, and it is in an objectively indeterminate state. Because we can see through the picture, what we can literally see is this, and we can't say whether that's a picture of a chair standing up or a chair lying down. It's in a position, a state of superposition. It is two coexisting objects, one standing normally and one knocked over. And we're saying that each drawing represents, and he's very specific here, one branch of the superposition. So I'm going to call that branch number 1, and that's branch number 2, and that's branch number 3. And I understand that. Mm-hmm. Now, if we remove one of the drawings so that only one remains, then the chair is in a sharp state. Okay? So because we're going to talk about this, we can either be in a superpositional state, mm-hmm, or I'm going to go off the board here. There we go. Or a sharp state. Well, if there's just one of them, I'm going to draw it here. Can I draw it there? Yes, yep. Just about. And that I'm going to call a sharp state. Okay, so far so good.
Yeah.
Right.
And just to explain, so in quantum theory, this notion of superposition is related because when a particle on the subatomic level is not observed, it's quantum theorists will say it's in a state of superposition, which means the chair is both standing up straight and it's knocked over at the same time. This is known as Schrodinger's cat analogy, right? So Schrodinger used the analogy of, okay, if you put a cat in a box so that it's not observable to the human being, at least, it's both dead and it's alive at the same time. Now, what most quantum theorists who go for this superposition aspect, which is controversial, I don't believe it, kind of thing, right? I don't believe it myself. I will explain my view after Hugh, but just going with that for the moment, once we open that box, then the states collapse into one state. The cat is either dead or it's alive. It's not both any longer once that observation is made. Now, Scott Hill is different. He's taking what's called the non-collapse interpretation of this quantum physics. So he's saying, well, actually, yeah, it remains, even with us, it's in both of these states until the moment of resurrection. So is that correct, Hugh? Have I understood that properly in terms
I think that's broadly correct. Yes, I think that's right.
Okay. Okay. So
I'm almost coming to the end of this thing now. So we've got. So we know what I want to do is to, in my mind, clearly define his terms. So each of these is a branch. There are 3 branches. There is either a superpositional state in which the branches are all on top of each other, and there is a sharp state in which perhaps they all resolve into a single state. Now, these branches, he's got here, he said, imagine there's a third uh, picture added to his original two. And he says that this state, the state of the chair lying down, has a higher intensity. So if there are three possible states and two of them are the same, then the third state has a higher intensity. Obviously, the two states which are the same have a higher intensity than the one state. Now, this is where lights get a bit difficult to me, because he says, let's imagine we put an infinite number of sheets in the stack. So presumably, we don't know now whether they can be the chairs in an infinite number of positions, or whether they're all either in that state or that state. But either way, he says the intensity of a branch, that one or that one or that one, is the squared amplitude of the branch, and the intensities sum to unity, to one. So in other words, the intensities of these must be, I'm going to put them here, a third and a third and a third, because that adds up to one. And the intensity is the squared amplitude. So the amplitude of this branch is the square root of a third, which is about just over half. But I don't understand the maths, the maths behind that, let alone the physics. I can see that he said something, but I don't think it's true. I don't think it means anything. How does he know that the intensities of these things add up to one? How does he know that the amplitude of each one is the square root of a third? We get no actual mathematical justification for this at all. We're just landed with it and told, let's suppose this is true. But why bother? Why should we suppose it's true? It's got nothing to do with the rest of his paper. I wonder why it's there in the first place. And I feel that he's sort of, having started with something sort of vaguely mathematical, which doesn't actually mean anything, he then feels that he's justified in talking about everything else. But I'd like to just have another look at how related these two positions are in terms of crossing over from this position to that position. Now, as far as I can see, this position is entirely, as we say, physical, and this position is the mind state or the soul state or something like that, if you will. But then, if the physical state completely disappears, are we left with nothing but mind and soul? In which case, the three-dimensionality of heaven completely disappears, and yet we hear that we have things will be restored to us. The Catholic view in general is that we will have bodies in heaven, and I think that's sort of fairly standard doctrine, if not dogma. And I want to know is, when you die, are all your physical characteristics transferred into your other state? So if you die after a long and tortured time, so that you die in a state of complete physical degradation with blood pouring out of various holes of you, is that the state in which you are revived? And the answer, obviously not. When Jesus reappears, he reappears as perfectly capable of walking on his own. He doesn't shuffle aimlessly about. He's restored to a different state from the one in which he died. And I think people who fiddle about with physics too much, when you go from physics to when you go from physical reality to a supernatural reality, I want to know what happens to when, supposing you die by having your head sliced off. When you come back, is your head still sliced off, or has it been replaced? If you lost if a battle scarred veteran in a wheelchair who's lost both legs and one arm, when he dies, does he return as as a battle-scarred veteran with who's lost both legs and one arm? Um, People who've suffered, if some people go, ah, yes, but it won't be a literal physical state. It'll be, as C.S. Lewis thought of it, as being a kind of, I don't know, transmogrified physical state, a kind of ideal physical state.
Mhm.
But at what age are we expecting a person to appear in heaven? So if you were 6 and you were run over by a bus, are you 6 eternally? Do you look as if you're 6? And so on. The trying to get physics to re-establish a kind of perfect you, I think, is very difficult. I would stick to the supernatural if it was me.
Yeah, I totally agree with you that there are major theological and biblical problems with Scott Hill's argument for how he understands the resurrection. And in his paper, obviously, yeah, we have a body and we're a soul. Now, in his paper, he kind of just assumes, no, we're just physical. Let's just assume that for the sake of argument. So there is no such thing as a mind or a soul that can exist in a disembodied state. So he believes that right at the moment of our death or whatever, we exist in this superposition state where we're both dead and we're alive at the same time, and these never collapse. So even if somebody observes at the resurrection, God or someone observes it, there are these two states. But how do we get the resurrection body in this branch, so to speak? And that's where he gets into this issue of quantum tunneling, which is relevant for when we're going to be looking at Paul Bruney's theory for the shroud. But he says the branch where the body remains alive quantum tunnels into this branch where Jesus died, and that's the resurrection. So there's a physical body in both branches. One dies and it rots or rots away into nothingness, whatever happens to bodies. And then the physical body in the other branch where you didn't die quantum tunnels into this one. And that's what Scott Hill's argument is for the how the resurrection works from a purely physicalist perspective. And like you said, I just find there are so many biblical and theological problems with that. But yeah, go ahead. What were you going to say?
But yes, so presumably the uh, the quantum tunneling, the body which goes forward in, or which tunnels through into this body, into the physical body, um, is recovered. It's not so badly injured that it can hardly walk, or in fact is dead. No, it's alive. So what? How has this one developed in such a way that when it transfers, you end up with a living person? And again, I would say, it's not just if it works with Jesus, does it work with everybody? How does that work in terms of in terms of ordinary people? I
Mhm.
mean, when people die, if they go to heaven, we don't see them on earth. Whereas if that's the normal thing that happens, then we should see not only Jesus walking around, but everybody else as well. And I mean everybody, all whatever it is, 150 billion people have ever been. Um, why have all they disappeared, but only one of them came back on himself? Now you might say, oh yeah, but both their bodies completely disappeared. But in that case, you lose the concept of heaven altogether. So I don't think it's his postulate is logically possible.
Yeah, yeah. I think there are logical, metaphysical, and also even physical problems because his understanding he takes this non-collapse theory, which I think is just a false theory kind of thing. And I would say even with regards to superposition, I would reject even the majority view, which the collapse position, right? So most people take kind of the collapse, right? So Schrodinger's cat. Okay, you have these two branches where he's both dead and alive, and then when you observe Schrodinger says, "Oh, it collapses into one or the other state. He's either dead but he's not both." Scott Hill is saying, "Well, no, even then it never collapses. He maintains both branches. It continue to exist." But I want to
No,
reject.
Schrodinger did. Schrodinger didn't. Schrodinger, his
He says it
idea was that
collapses.
you only had one in the end.
Yes, for him, he takes a collapse view, and that's the majority view. I would
Yeah.
reject both views, though, and just want to get your take on this. I think, look, when you have something like mashed potatoes, we're talking about the probabilistic thing is talking about its potential states. They don't actually exist in any ontological sense. So, look, potatoes have the potential to either wind up as French fries or as mashed potatoes.
Yeah.
They're not actually both mashed potatoes and French fries until I look at it, and then it becomes one. So I think there's this confusion between there's an assumption that, oh well, until we observe it, it actually exists as mashed potatoes and thing. And I think that's total nonsense, metaphysically and physically speaking. I think that no, it had the potato is a potato and it has the potential to be one or the other, depending on what happens to it. But yeah, what's your take on superposition since that's relevant?
I think Schrodinger and I think the superpositionists um, are thinking in practical terms, are putting an awful lot onto um, it's as the world being a relative place. Let us suppose, and funny enough, we don't have to have all this business about cats and poison bottles and things like that. I can just ask you, whatever room you're in now, there's another room that you're not in and you can't see. Now, I'm going to ask you, is there a spider crawling up the wall of that room? And your answer, I hope, is going to be something like, I don't know.
Mhm.
And that is all you need. Maybe there is, maybe there isn't. And what's more, you're not going to find out unless you go through and have a look and go, no, there isn't. And it would be Schrodinger's, well, not perhaps not Schrodinger himself, because he understood all this very well. But it is sometimes the collapsed state hypothesis that until you look at something, you can't be sure whether there is a spider there or not. Now, in your hypothesis, you would say it doesn't matter whether I can be sure or not. There is or there isn't. If somebody else might be there.
Right. Right.
But from a lot of quantum physicists' point of view, the fact that you can't check something means that you can't be sure whether that state is there or not. And we might, as well, we can just as easily pretend that the state is in both positions. And what's more, and this is where life gets really weird, and that is that we can demonstrate in some cases, and this is the double slit experiment that you're saying. The double slit experiment actually shows that the spider is there and not at the same time.
So so
That's
no
really weird.
so no it doesn't. So and I'm going to play a video clip. Here's where I would say, okay, so first of all, we have to admit this from an empirical standpoint, physically speaking,
Mm-hmm.
both interpretations are what scientists call empirical equivalents. We cannot adjudicate which hypothesis is true. What mine, where it's the potential thing, versus no, they actually exist in a state of superposition. These are empirically equivalent. And I think that's you agreed with that by saying, well, can you tell me empirically, is there a spider in that other branch or not? Now, the evidence supposedly given for superposition, I don't think helps us to empirically decide. And the reason I favor mine is based on philosophical or metaphysical reasons. I think superposition is nonsense metaphysically, but I admit physically and empirically, there's no way to adjudicate, including with the double split experiments. And I just want to play a video clip of that for the audience who might not know what exactly is this. Basically, the double
Yeah,
slit
good idea.
experiments prove that subatomic particles exist as both a particle and at the same time as a wave function, probability wave function. So let me bring up a clip just to explain that.
Yeah.
So here,
I'm just going to get a rag so I can wipe my screen.
okay.
The double slit experiment defies our understanding. It involves a laser shooting beams of light particles called photons at a screen with two parallel slits. If we mark all the spots where the photons hit the second wall, we should expect to see two strips to correspond with the two slits. But that's not what we see. Instead, we see an alternating pattern of light and dark bands. This is characteristic of the behavior of waves that pass through both slits simultaneously, interfering with each other to create the pattern on the second screen. The bright lines are where the top of waves meet, resulting in a more intense or brighter area on the screen. The darker bands are where the top of one wave meets the bottom of another, so they cancel each other out, resulting in a less intense or darker area on the screen. Here is a photo of a real interference pattern. The original double-slit experiment was conducted in 1801 by British polymath Thomas Young. Since then, it's been performed with various types of particles, including electrons, and they were found to behave in the same way. This phenomenon occurs even if the photons are fired one at a time, which suggests that the photon is interfering with itself as it passes through both slits at once.
Physicists were so stumped that they decided to observe which slit the particle went through.
And that's when things get really weird. When scientists used a measuring device to observe the slit that each photon passed through, the interference pattern disappeared, and the photons started behaving like particles. Instead of the spectrum of light and dark bands, we see two bright bands, indicating that the photons chose one slit or the other. So light can display characteristics of both particles and waves, known as wave-particle duality. It appears that light decides to behave as a wave when it's not being watched, and acts like a particle when it is being measured.
Okay, so I think that kind of explains. This is what the observations prove there. Again, that observation is consistent with what I'm saying when it's a probabilistic wave. So it's saying, in the middle, you can picture a bell curve or something. So it's most likely that this particle is here or something like that, or can be found there. It's less likely that it's found in this position near the bottom of the bell curve or something like that kind of thing, right? So this probability wave is describing its potential states. This, again, picture the potato. Okay, as a wave function, we're just saying, okay, it's potentially mashed potatoes or it's potentially French fries kind of thing. That's what the wave patterns prove, but it doesn't prove that it is, in fact, both mashed potatoes and French fries. That's just an assumption. The empirical evidence does not tell us that at all. That's my only point with respect to this superposition idea in the first place.
Tunneling is a phenomenon in the realm of quantum mechanics, where a particle crosses a gap or barrier that it shouldn't be able to
To a
cross.
certain extent, that's right.
Yeah.
Oh, can you hear me? I've got a sign saying my internet connection is unstable.
You're coming through now. Yeah, we can hear you.
There are various things wrong with this experiment, which I don't know enough about. Firstly, the wave pattern that you observe if you have two slits and you just excite electrons off the end of a thing certainly happens because you can experience it yourself. And I did this in high school when we played two loudspeakers playing a sound. And the loudspeakers were, as it were, here and here. The sounds were exactly the same in terms of frequency and interlocking. And if you stood about 30 meters away and you just walked in a straight line, you can hear the sound going woo 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 woo, showing that the interference pattern of the waves works. So that's something that I personally experienced, and anybody can do, and a lot of high school people have done. You may have done it yourself. And we know that happens because you can see it. That row of little red dots in the video showed that that's what happens when you squirt electrons. Now, what I want to know is where these electrons come from and how do they know where to go? I'm suspecting that each electron is negatively charged, and that the plate on which they are, I mean, the electrons are negative, and the plate on which they are standing is positively charged. So the electron, if there was nothing in the way, would just go directly towards the plate and make a mark. Now, if you block it, I don't know quite what happens here. I don't know if this plate is positively charged or why the electron doesn't come whizzing along here, arrive here and stop. Why would it go that way? Why deviate if it's, I mean, it would go the shortest way. And I don't really know what the answer to that is. However, I do know that if electrons are released one at a time, and it's possible to release the electrons one at a time, we still get this pattern. But I want to know, if you release an electron one at a time, what happens to do any of them go here? And
yeah, I mean, they do, because otherwise
goes in that direction. Why should they go particularly through those slots? I need someone who's done more practical physics than me to explain exactly what the setup is, which is never shown in films like the one you've just shown us.
Yeah, I don't. So I thought I understood. I don't understand if they release the electrons one at a time, because then, yeah, you'd be aiming it at a hole kind of thing, rather than like dispersing a bunch of electrons all in all directions.
Yeah.
The ones that hit the walls would be blocked, and then the ones that go through the holes, that's why we get those patterns when they're observed. But if it's one at a time, I guess they're just saying, yeah, they aim it one at a time at the holes to see, and they observe it. Does it create that pattern versus a wave when it's observed versus a wave thing when it's not? They would have to aim it at the holes, I would think. But fair enough.
Yeah.
So
I mean, there are practical things which I don't really understand, but I do sort of see that the two sort of things here. Firstly, from your point of view, or from my point of view, or from any scientist's point of view, we can't know what's happening here or here, because the action of observing something will change it, as indeed we spot. Now, what we didn't hear in that video is, how do you tell if an electron is moving past a detector without disturbing the electron at all? I don't understand that either. If you had a machine which detects things going past, what you would normally do, this is if you're at a supermarket checkout, for example. Here's a supermarket checkout.
Mm-hmm.
And I used to encourage my students to try this. There is a light beam going across to a detector. Mm-hmm. And as long as the light beam is shining at the detector, the motor is switched on and the box of chocolate is going along the motor. And as soon as the box of chocolates arrives there, the beam is stopped and the motor stops.
Mm-hmm.
And that's how a supermarket checkout conveyor belt works. And if you've got a decent, able to do these things, because unfortunately I can't do it at my local supermarket now because the COVID screens are blocking it. But I used to stand there looking innocently out of the window, doing this with my finger, and the whole conveyor belt would go and go forward in jumps, disturbing everybody.
Teddy is right. You're a troublemaker. Teddy's right about you.
Yeah. Well, then I used to encourage all the children to do it as well. But to explain afterwards that what they were doing was testing a physical hypothesis.
Okay.
But now, let us suppose, as indeed we may be, that the light was traveling in every possible way. I mean, why should it be blocked buy a box of chocolates, why doesn't it go this way? What makes it travel necessarily in a straight line? Because we know that light travels in a most peculiar way, in such a way that we can normally detect what's going on in between the source and the detector. Now, the light's not going to make a lot of difference, perfectly honestly, to a chocolate box. But if it was something incredibly small, like an electron, then the action of detecting it would push it somewhere, if that was the system that we used. Do you see what I mean?
Mm-hmm. Yeah, I get it.
How do you detect a passing electron? Do you hit it with something, or does it hit you, in which case it loses energy? So I don't know how you can do that. I mean, that they had a little sort of detector which flashed. How does that work? I don't know.
So yeah, so you're kind of pointing out there, agreeing with me. Look, there are a lot of holes.
I'm just saying that there are experimental difficulties which are not explained to me.
Fair enough. Yeah. But yeah, so my point is the interpretations of this data, there's a lot we don't know, and there's a lot of assumptions being made. Now, just before we get into transitioning into Paul Bruney and his notion of the shroud, there is another phenomena, quantum phenomena, that we need to understand, and that's this notion of quantum tunneling, because that's crucial for Paul Bruney's theory about how how this explains the shroud images. So let me just play a video on what quantum tunneling is.
Thank you.
No problem. All right, so here we go.
Quantum tunneling is a phenomenon in the realm of quantum mechanics, where a particle crosses a gap or barrier that it shouldn't be able to cross in classical terms. Let me explain this with an example. Imagine you're sitting in your living room with your cat. Suddenly, the cat jumps up and dashes to one of the walls of the room. When it reaches the wall, it starts to sniff and lightly touch it. After a minute of doing this, it goes around the wall, out of your sight, and into the room to investigate what's on the other side. The cat wanted to see what's on the other side of the wall, but it had to go around the wall to be able to investigate.
Now, just one thing I want to clarify about I don't like this. There was another video with Neil deGrasse Tyson where it describes this the barrier, this energy barrier, as physicists call it. You can imagine it as a hill or a wall, right? So how could you get over this barrier? Well, you could go over top of it, or you can go around it as this cat did. The point is, though, it takes energy to be able to go over the wall or to go around it. And what physicists are with quantum tunneling, there is an insufficient amount of energy to be able to get around the barrier or over top of the barrier. You can't do it, physically speaking. You don't have enough energy to do so. But with quantum tunneling, they're saying, but yet it's like the cat, just that magically, or the particle just magically appears on the other side of over top of the barrier, or within the barrier, or on the other side of the barrier. And that's quantum tunneling. It tunnels through the barrier. But again, I'll continue playing the video clip.
But it had to go around the wall to be able to investigate. Now, imagine if the cat could simply disappear and then appear on the other side of the wall. Sounds like science fiction, right? This is an oversimplified analogy to explain what happens during quantum tunneling. This concept seems paradoxical from a classical standpoint because it allows particles to pass through a barrier without needing to have sufficient energy to cross it. The rules of quantum mechanics state that the quantum state of material particles, such as electrons, can be described by a wave function. In classical terms, describing a particle's state with a wave function may seem strange. This is where wave-particle duality comes in. This is a concept in quantum mechanics that suggests quantum entities can exhibit both particle and wave properties, depending on the experimental conditions. In simple terms, this means that a particle, like an electron, can behave as both a particle and a wave. This is why a particle can be described as a matter wave. It's this matter wave that can be represented mathematically as a wave function. In simple terms, Particles such as electrons are not just points in space, but also exhibit wave-like properties. In the classical world, particles can be precisely located in 3D space using x, y, z coordinates. However, in the quantum world, which deals with elementary particles, the location of these particles is described in terms of a probability wave. This wave indicates the point where the electron is most likely to be found, the crest, and least likely to be found, the trough.
Okay, so this is the point, right? So when we're not observing this subatomic particle, because again, quantum physics only applies to subatomic particles, not atomic or bigger objects, right? And stuff, we know that. That's classical physics. But when a subatomic particle is not observed, it takes on the shape of a probability wave. So if you imagine the barrier right here in the middle or something like that, just for the sake of argument, this wave is saying, well, if we were to suddenly observe, turn on our eyes and observe the particle, the wave, it would transform into a particle and it would have a known state. And the most likely place it would be right here at the crest of the probability wave. We would be most likely to turn on our instruments and detect the electron right here, right in the middle, tunneling right in the middle of the energy barrier, for example, or in the middle of the hill or something like that. But it's not necessarily there. It could be that we would find it. It's not impossible, even though it's very improbable. We might be able to observe the particle right here on the other side of the energy barrier and stuff like that. So that's what quantum tunneling is. Like you start on this thing, but through tunneling, it's almost like if you suddenly observe an unobservable particle, it's possible. There's a 1% probability you might just find it on the other side of that energy barrier type thing. And again, that's assuming this understanding of superposition that before it's observed, the particle is actually in all places. It's in all of these places. It's assuming superposition. Once you observe it, it transforms into a particle and is either at this place or it's right here or wherever it is, kind of thing. And that's the superposition state that they're assuming. Again, I question that. I don't believe it's actually on the other side of the wall. But yeah, does that make sense in terms of what quantum tunneling is, Hugh?
No, I don't think that most probable position gets it perfectly. Well, I'm not sure. I don't think I'm going to get it perfectly either. But can you see I've got a ball here.
Okay.
And I've got a block of ice here.
Yep.
And the temperature difference between the ball and the block of ice is such that the ball is not going to go through the block of ice terribly easily.
Mm-hmm.
Now, because of this, when the ball meets the block of ice, let us suppose that the ball could take energy from the block of ice.
Okay.
So the ball is now 12 degrees Celsius and the block of ice is at -10. Now, the difference between those two is such that the ball melts straight through and gets to the other side. And you might say to yourself, well, in that case, we could measure the temperature of the ball and we could find that it had magically got hotter and therefore it had gained energy. And we don't. We find in quantum tunneling, we don't think it's got any more energy than it had before. And the point about this, and Paul Bruney mentions this, is that after the ball's gone through, it gives its energy back again. So the ice returns to being 0 degrees centigrade and the ball returns to being 2. So it's an instantaneous acquisition of enough energy to get through and then giving it back again.
Okay.
And that's and perhaps another way of looking at it.
Yeah, I like that.
The superposition of electrons, and this is partially something to do with it. Down here, I've got a picture of an atom with some electrons, and this is more or less the primary school version of an atom, which has the electrons whizzing around. It's slightly different from a primary school in that electrons actually go around in 3 dimensions, not in the 2 like a little solar system. But of course, the electrons aren't really in any of these places. These are sort of probability gradients, if you like. So the electrons are most likely to be somewhere around there, but not necessarily in any of those places exactly. That's what this probability curve that you drew was all about. Where in fact is the electron? And I think that's another way of looking at it. But either way, the point is that with quantum tunneling, we can observe this. We can, or we can't necessarily observe it, but we can explain a natural phenomenon because of this. And the phenomenon I would like to explain, or at least to try to explain, is photosynthesis. Because what we know is that when light hits a bunch of chloroplasts, it makes them carry out the chemical reaction of photosynthesis. And the funny thing is that if the energy requirements are here, and here, we should get these ones working quite well, these ones working rather less well, and these ones not working very well at all, because the light's all hitting all these others. But rather to our surprise, all of them seem to work equally well. The energy loss between the amount of light hitting something which is carrying out photosynthesis and the energy required to produce the chemicals as a result of photosynthesis, the glucose, there's almost no loss. So how can these electrons bounce around without losing energy? And of course, the answer is twofold. Firstly, if they are in a whole variety of different states, they can sort of experimentally go every possible way very efficiently, and the one which is resolved is the one which works best. Or alternatively, we can say that as they reach something which they want to go through, they borrow energy from it, go through it, and give the energy back, and then they carry on with the same amount of energy as they had before, and they haven't lost any. So that's
that really helps.
Another way of looking at quantum tunneling, and this actually works in real life. That idea explains why photosynthesis is so efficient.
Gotcha. So quantum tunneling,
wrong idea, but it is an explanation.
Gotcha. So
Yep,
it's a real observable phenomenon. So I just want to kind of turn it to you, and thanks for explaining the energy part, because I didn't understand that part totally. So that I loved your example of the ice and the thing that explains it really well. But I
think that's what Paul Bruney would say. Yeah.
So how does Paul? Okay, great. So how does Paul Bruney apply this notion of quantum tunneling and quantum physics and use that to try and explain the Shroud images? Do you want to just take some time to explain what his theory is with respect to the Shroud images and what your take is?
Well, at this point, I sort of lose track of him, because we've got this. He states we simultaneously coexist in two different universes: observable real time and space, and unobservable or imaginary space time. But I have no evidence for that, and I don't know what he means by it. It may be that that exists, and that there is some sort of mathematical correspondence to it, and I can sort of imagine it, but I don't know that it's true, and I don't know that it's justified. And the trouble with coming up with an imaginary idea is that it has all sorts of corollaries which go with it, and one is not able to say how those corollaries work unless you really understand what his idea is. And I didn't understand that at all. What I found particularly confusing, I suppose, as it got towards the end, when it comes to turning into taking something from a body and putting it on a shroud, is that practically everybody, in fact, I think absolutely everybody, thinks that who believes that there is action at a distance working in the case of the shroud, doesn't work with people like me who think that the intensity difference of the image is based on pressure. But if you think that the intensity difference is based on distance, then you must assume some sort of collimation. And the most normal way in which people investigating this have assumed that the collimation is vertically up and down, possibly following gravity, or possibly following an electrostatic difference between the top and the body, of top and the bottom of the tomb. And then there's Dr. Lavoie, who thinks that the man was vertical, so that the collimation was horizontal. But I don't know that he has any physical explanation for the collimation being horizontal, which is fair enough, because it would take a miracle to stand a dead man upright in the first place. So that sort of thing is not accounted for in Paul Bruney's paper at all. And I just, he goes on and on about the shroud image appears to be the result of real states in real time. But it doesn't appear to be. It is. You can see that it is. I really don't understand. I wish I had him here to I could ask certain questions of it. But no, I'm at a loss for me to understand that it means anything.
Okay, so
I will say that physicists such as myself and my colleague Albert Einstein, such as, well, all physicists, we explain things which turn out to be intellectually quite complicated, but they can be explained in very simple terms. Einstein wrote a whole book about trains in the valley being looked at by people on the hillside, and you understood immediately that somebody in the train who's bouncing a ball up and down in his hand, from the point of view of the person on the hillside, sees the ball traveling in a huge arc like that, because the train is moving along. But the person in the train just sees it going up and down. Your frame of reference really is observably different depending on the observer. And similarly with my analogy of the ball and the ice and things like that, these things are really easy to put a simple explanation across. And if you're going to start going on about quantum theory, you've got to understand, you don't have to understand the theory so much, but you have to understand your own interpretation of it really clearly. And I don't think that this paper demonstrates that Paul understands what he's talking about. Let's say that he doesn't understand what he's talking about, but the paper doesn't demonstrate it. That's all I can say, really.
Okay, so just to try and get a grasp on this for the audience, kind of thing. So what, in layman's terms, his theory would be this, right? So you're saying that Jesus is dead, and at that moment in the tomb, he's covered in the shroud and stuff like that. And then you're saying the body, he posits that the body has to be vertical, like floating, kind of like Gil Voice says. It's not horizontal where it would be.
But no, he doesn't mention that at all. Okay. He doesn't specify that at all. He's merely talking about the shroud image is the result of energy introduced from that part of our space normally hidden from view. But so I don't know that any part of our space that is normally hidden from view.
Okay, so before we get into that stuff, though, what is he positing that the body of Jesus, I understand it, the subatomic particles, I guess, in the body of Jesus all quantum tunneled through the Shroud of Turin, and then this left, and the energy kind of thing was phase inverted, so that energy from this quantum tunneling created images in real space and time on the shroud. First of all, is that what he's kind of saying in a nutshell? That's the body, the subatomic particles of the body quantum tunneled during a phase inversion event, and that created energy on the shroud that left images.
It may be. I'll interpret it something like this. I'm going to imagine, as I do, a dead body with a cloth on it. And I'm going to imagine that this is any dead body with any cloth over it. And that at the point either of at some point during decomposition, shall we say, various particles come off the body. And I'm going to suppose, for no particular reason, that they come off the body vertically collimated. Now, those particles have the energy that they have, and they go through the shroud. Quantum tunneling is not a peculiar thing. It happens all the time, and we don't notice. And because they go through the shroud, and they, when they hit the shroud, they take energy from it, and they go through, and they put the energy back, and they carry off into the distance. Yeah? But in the case of Jesus, the particles arrived on the shroud and took energy from it, but they didn't give it back. They used that energy to burn an image on the shroud.
Mm.
That and if you sense that the energy then dispersed in the normal way. That's the only interpretation I've come up with that seems to make any sense at all.
Now that interpretation, so this is, by definition, it is a supernatural hypothesis because he's positing quantum tunneling working in a way that it isn't known from quantum physics or naturally to behave. There's this phase inversion of the energy where it's not returned. It's so this by, and plus you're positing vertical from the body. These particles only come out vertically. So this is by definition a supernatural image forming hypothesis. Is that correct? It's not a.
The shroud image only momentarily involves the past dead state. It engages only the very last moment of imaginary time, which is the dead state, and the following real-time resurrection. That is, there was no life in the body for 2.5 days, and then real life suddenly appeared with a flash of some kind emitted from the body. And that's this flash that, as a result of perhaps non-quantum tunneling, has resulted in the in the discoloration of the cellulose. But I don't see that makes any sense. You don't need quantum stuff. I mean, I think Paolo Di Lazzaro's idea that the whole body emitted, and I think Bob Rucker's come up with it now, that the whole body emitted ultraviolet light works better. It's simpler, and it also results in a discoloration of the shroud.
Now, so I'm curious about this because I know Paul Bruney, in terms of experimental results kind of thing, right? So he mentions a test at some. I admit I didn't have time to read over that, but I'm just kind of wondering if we grant, for the sake of argument, this process happened the way Paul Bruney is positing, would it actually create images on the shroud in the first place? Forget about whether they compare to the shroud images and the minimal relevant features. We'll get to that, but will it actually create images of a body on the shroud? Is there any experimental evidence for that, or no?
You see, he doesn't actually demonstrate his test very far. I will read it to you and try and illustrate it for our listeners. It is proposed that two groups of positively electrically charged fluids be placed in close proximity to each other on level, smooth surfaces, e.g. microscope slides, each group respectively representing a new positive input and a new positive output, resistively connected to the ground. In this simulation, the added positive output constitutes a new current flow. But that doesn't mean anything to me at all. So he wants two positively electrically charged fluids next to each other on a microscope slide. We might call this a microscope slide and suppose that we can positively charge them. Well, I've got that far. Each group represents a new positive input and a new positive output. Well, I don't understand why it represents a positive output resistively connected to the ground. Do we connect this to the ground, in which case it would immediately go to zero? Let's suppose we do. So we take this and we ground it, and now it's not charged. And now there will be an electrical flow, but in this simulation, the added positive output constitutes a new current flow. Well, if there's a current flow between here and here, there'll be a current from there to there, but electrons will flow in that direction. But so what? I'm inclined to say I don't understand how this works. Sorry.
Gotcha.
And it just doesn't, it's not a practical setup. If it was a practical setup, I could go to a laboratory and do it. But there's no way that this explains anything at all. It's not a test. It's a way of, I don't know, trying to explain how a test might work if somebody could come up with a better idea. But I can't envisage it, which may be that I'm not clever enough. And it would have been nice to talk to Paul Bruney, who could explain it more clearly.
Yeah, hopefully. Again, if something happened, Paul or whatever, if there's a reason,
he may be able to watch this later on, and comment either in the comments underneath or by an email to you and say, no, this is what I meant by this, and this is what I meant by this, and this is how I would set up my test if I had the finances. But he hasn't done so far.
Awesome. So yeah, no, and obviously we wouldn't expect there to be any experimental proof because naturally they don't leave. Quantum tunneling occurs all the time, but it doesn't leave behind images and stuff like that because he's having to posit this supernatural phase inversion in order to get the energy not to return to its original source, but to create these images and stuff. So we wouldn't expect really to find confirmation. Okay. Well, let's grant his technique for the sake of argument. Let's say it would create images somehow. The energy would create images. How would it do in terms of explaining the shroud's minimal relevant features? Can we adjudicate anything? Would it create negative images or semi-negative images at all?
We would no. Well, I don't know. You see, if the world is a very messy place, and in between the body and the shroud there's a lot of air all jiggling around, and I don't see, I mean, the quantum bouncing around all of that. If we just assume that they work as light and say that it would be ultraviolet light, then yes, I suppose we could have that sort of negative inversion. But if you're going to start invoking quantum tunneling, I don't know why the shroud image should be a purely surface phenomenon.
Superficial.
I mean, the whole point about quantum tunneling is that it tunnels. If you see what I mean.
Yeah, exactly. Yeah. Okay. Well, so superficiality, even on the fabric level, let alone the thread and fiber levels, it would not achieve that. Now, what about double?
As I understand, it would achieve that.
What about double superficiality then? Because from my understanding, I never included this as a minimal relevant feature, but from my understanding, on the fabric level at least, you yourself have admitted that there is an image on the backside of the cloth. And from my understanding, you say that it is superficial on a fabric level, but we can't prove it's superficial on a thread and fiber level. First of all, is that correct? Do you accept double superficiality on any level? Or
well, yes and no. It's possible that some color appears on the back, but remember, if you take, shall we say, a red T-shirt, well, no, not because they're red all the way through, but something that's red on one side and white on the other, a cloth that's red on one side and white on the other, and quite clearly the red doesn't come through. But if you hold it up to the light, you can see the design, because the light shining through it will produce it. Will show you that image. In fact, I mean, an extraordinary, and I was going to say, it also works with reflected light. So if you lay this sheet down, red side down, onto a table, and you take a picture of it, it still looks pink, because you've got some light coming from at the outside through the material, bouncing off the red and coming back again as red light through the material. So it might still look pink. And you'll know, well, perhaps you won't know, but I'm sure you do, that film stars and girls going to the Oscars and things like that are often very worried if they're wearing some particularly sheer sort of material, that photographers will take photographs of them, will be able to make out, I mean, their intimate details, because the light's going through the dress, bouncing off their bodies and coming back again. So you can see a great deal more in the photograph than you can if you just look at them, which is because these powerful flashes that they use. Now, no one, I think, has actually looked in detail at anything that there might be on the backside of the shroud. And even Julia has had to carry out the most extraordinary amounts of photo manipulation of light and dark to be able to make out bits of the image. But it may be that simply the darker bits of the image are visible because they are visible through the threads of the linen. However, it's also just possible that there is some actual image on the other side. And we'll have no way of knowing until we actually get a hand lens, is all you would need probably, and look at it really closely. I say a hand lens because with a hand lens, you block off most of the reflected light. So it's not likely to go all the way through and bounce back again. You just get light off the surface. And that would tell you whether you thought you saw any discoloration or not.
Okay. So
now,
that's
the best example, the best illustration I've ever had of how double superficiality might work is actually with his evaporating solutions. Now, Rogers imagines a cloth soaking wet, and with something in solution, and it evaporates from the outsides of the cloth, and as the solution evaporates from the outside, what's inside evens itself out. So we get the solution spreading itself out towards the outside of the surface of the cloth, and then evaporates from there, and slowly the liquid inside migrates outwards until there's some sort of equilibrium point in which there is hardly anything inside, but the solution, together with its solute, has all moved, and the solute has ended up on the outside like that. And in that case, if you were to, as it were, very briefly in an oven or something like that, the starch on the outside might char, leaving the cellulose and cloth, the cotton, the linen on the inside completely char free. And in that case, you could get a doubly superficial deterioration of the cellulose. That's the best way that I've seen it. Now, both Julia and Paolo, I think, have speculated things involving electrostatic discharges, which again, in a slightly different way, they've imagined that where there is as it were, a phase transition, you get an energy transition. So if you've got some sort of electrostatic charge, which I'm going to assume is positive at the top and negative at the bottom, then the electrons come through here, and then they go through there, and then they disappear out there. And as they hit the surfaces, that's the point at which they lose their energy. Otherwise, they just carry on through. Now, I'm not sure how true that is, but that would be another possible way of doing it. However, if I look at Mark Evans's pictures, photographs, and Giulio himself points these out, we can see where the that's not a very good example.
It's hard to see that for some reason.
Oh yeah, well I can't really see it myself, and I haven't drawn it terribly well. But where the if I just draw two threads like that, there we go. We can see that the color disappears deeply in between the threads. It's not just entirely on the surface, it's down here as well, which suggests to me that there is a bit of slippage, and it may be in the darkest parts, it's gone right through and come out the other side.
Interesting. And
that's my opinion.
And one thing I'll just note is so it looks to me, yeah, so double superficiality isn't actually confirmed. What you were saying is that, well, there is, I've seen you've seen evidence that there does appear to be an image on the reverse side, but that could just be the reflected light coming through.
I think so.
We haven't proven that there is actually
yes.
Okay. Okay, so that makes sense. But assuming double superficiality is
never thought of it.
Assuming double superficiality is true, two quick questions. So, number one, I know that your image forming hypothesis, Giulio noticed that it wasn't superficial on a fabric level. The pigment particles came through to the other side. Is there any way your image forming theory could explain double superficiality then? Because I know you say, well, it doesn't penetrate the threads or the fibers, but it goes through all the way to the backside of the cloth. Do you think that you could?
Yeah, well, it goes right between them. I mean, if we look at a cross section of the shroud, it looks like this. the line across this line is maybe a warp thread, and these there we go, and the circles are the weft threads. Do you see what I mean?
Mm-hmm.
So it goes across three and then under one, and then across three and under one. Mm-hmm. And so when we look down on the surface, we see mostly these threads here, and mm-hmm. it's on the surface of this that the image mostly forms. Now, although and choose another color. Like all good teachers, I use these pens until they completely run out and then nobody can see them. But if the image forms on the surface of these threads, it falls down between the threads. Oh, it may do, and comes out the other side.
Mm-hmm.
Something like that, but it would only come out very faintly, but you would see it disappearing into the cracks between them like that.
Okay.
Which indeed you do. On the Mark Evans pictures, it's quite obvious that the image dives down into the clefts. Obviously, you can't see what it's like absolutely underneath because he's only photographing it from on top.
Okay, fair enough. And the other question, so Paul Bruney's hypothesis, then again, granting, let's say somehow is there any way his quantum tunneling theory could create double superficiality?
I don't think so. If you cast your mind back to my little diagram of photosynthesis, which had a row of green dots. Oh, there we go. That's what happens when you put green on top of red. So the green dots were like that. Now, the point about photosynthesis is that all these dots are equally efficient in terms of collecting photons.
Mm-hmm.
Now, if we suggest that these are perhaps the atoms of the shroud, then the surface here should be equally efficient as the middle bits here and the surface here. So you wouldn't have it just deteriorated at the top and the bottom, you'd have it deteriorated all the way through.
Gotcha. Okay. All right. So now we covered the vertical mapping that just wouldn't happen naturally. So that's a supernatural assumption he's having to make, because otherwise quantum tunneling, the electrons would quantum tunnel out in all random directions, including encoding his body
Certainly,
size,
that's right.
body
Yeah.
sides and top of the head and stuff like that. So that's inconsistent with the Shroud unless he assumes some kind of supernatural input. What about the three-dimensionality of the Shroud's images? Would Paul Bruney's hypothesis recreate that in your view?
Yes, yeah, if it worked out that whatever it was, because we don't really know. I mean, is he talking photons? I suppose he is. And if they were traveling, I mean, at the right um, frequencies and wavelengths, and I think this is Paolo Di Lazzaro's point. Um, the point is that supposing we imagine it's some kind of radiation, which is quite trendy at the moment. Now, there's a Frenchman called Donnet, who thinks that the radiation was infrared, and there's Paolo who thinks that it was ultraviolet. The point about this is that at certain frequencies, the radiation is attenuated very strongly by distance. And you have to make it so that in air, a light beam, or shall we say a photon beam coming from this finger doesn't reach this finger. Now, you might say to yourself, well, let's have a go. For example, if I held a red hot poker, supposing this finger here was actually a red hot poker, which I shall draw by coloring it red. I'm sorry to treat all your audience as if they were children, but I'm used to teaching children. Here we go. I have a red hot poker here, and I bring my finger up. Now, I might not, with this finger, be able to detect the red hot poker because the heat, the infrared radiation, which is what heat is so attenuated in the distance between the two fingers that there's nothing left here. And that's the point. In order to get the 3D or the photographic pseudo image, you've got to have radiation which doesn't work through air over that much distance. When it's this far apart, it creates an image. When it's this far apart, it creates not much of an image. And when it's that far apart, it creates no image at all, because the energy of the radiation dissipates as it goes through the air. And this is why, funnily enough, this is why the resurrection could not have been achieved with a burst of light, because light is exactly the same. It's not attenuated through the air at all. Otherwise, I would disappear in the distance between my face and the camera. And as you can see me. So light hardly attenuates in air at all. So you have to choose a radiation which works. And he doesn't discuss this. Paul Bruney just mentions photons, which might be photons of any energy or any wavelength or frequency. But it's important for the whole concept of the image that you choose a light which is attenuated in air.
And now with quantum tunneling, it would avoid all of that altogether, I would imagine, right? If under his theory it goes into this imaginary realm or something like that.
Well, we're not sure whether he's talking about electrons or photons or what. Excitons, quantum people often call them. But without him specifying, we can't say. He doesn't mention frequencies of any kind or wavelengths or anything.
Okay, but you're saying with respect to the three-dimensionality, depending on what subatomic particles he picks for doing the quantum tunneling, it may or may not work, or it just okay, fair enough. What about body image uniformity? For example, I know you deny uniform intensity of color, but there's also the max densities of the back and the front side. Would we expect uniformity of body images under Paul's theory?
You tell me. I mean, if the whole body, and again, it's you just have to speculate. Does the whole body radiate whatever it is that it radiates in a similar way? In which case, the uniformity would be the same. If the hair the nose, the fingernails, the teeth. Depends whether there's bones underneath or just flesh or whatever. Um, if this made no difference, if the whole body behaved as if it was just made of one single blob of jello, then then I suppose uniformity would be maintained perfectly.
I don't see that working without supernatural input, because so that's
Oh,
again
there's almost
because
there's almost nothing about this which works without supernatural input.
yeah, because
But
the
then the radiation theories are exactly the same. I
yeah,
mean, at least
correct. But I'm just yeah, I'm
they're a
just
little bit
saying
more conformable. The question is how much supernatural adjustment do you need?
yeah. So that's what I'm meaning. He's it's more ad hoc than the radiation, because he compared to Bob Rucker, who has the initial supernatural assumption, maybe a second one by saying the radiation is vertically collimated, depending on how you count the ad hoc component. This guy, Paul Bruney, has a lot of supernatural ad hoc fixes for
I'm
uniformity,
afraid, yeah.
vertical. There's more compared to radiation with Bob. So that's what I'm saying. Yeah, for uniformity, because otherwise on that probabilistic curve, maybe it'll tunnel and it'll end up in the same spot. So you have two energy producing tunneling particles in one area
It's fine.
and
Yeah.
three in another, and that would create differing color densities. So okay. Now what else? What about okay, well, what about the blood stains? How would if Paul's theory is correct for the body images, how would that interact with creating the blood stains? Say the blood was on there first, and or say the blood came afterwards. Are they compatible with a direct contact for the blood stains, or is there any problems there?
Um, well, again, you see, without a picture of it, of how, I don't think he addresses that at all. I mean, it may be or maybe not. It's not part of his thesis to address it in any way. Was the shroud in horizontal plane across the top of the body? Was it just dropped on top of the body? Was it wrapped around the body, tied up with strips? He doesn't address that.
Yeah, but let's say for the sake of argument, the bloodstains got on by natural direct contact. Let's just
Yeah. Well,
pretend
it's
that
yeah.
works. Would the quantum tunneling and this phase inversion of the energy, would that be expected to affect the bloodstains and be detectable in any way? Or do we just have no idea because it's not a process?
Well, it's difficult to imagine. Um, what you have to say is that you need some energy to make a piece of cloth turn brown, even the very surface of it, um, in a very short time. And we can express that if you choose the time to be 1 billion trillionth of a second, then you'll need the energy at a power of 1 billion trillion watts in order to get 1 joule of energy across. And this is Paolo di Lazzaro's idea. Now, if that amount of energy, if that amount of energy discolors this top surface of the cellulose to
Oh,
I don't know. I'm sure
you froze
Paolo.
there.
Oh, sorry.
You
If we can define the amount of energy necessary to discolor the cloth and then apply that amount of energy to a blood stain, we could then find out whether the blood stains as they appear are consistent with that amount of energy. And this applies to whether we're dealing with quantum tunneling or with ultraviolet or infrared radiation.
all right,
Have I
perfect. Perfect. So
got,
I think I've covered all the main minimal relevant features. It looks like this is obviously it even Paul Bruni intends it for it to be a supernatural theory, and that when it comes to that, sure, God can do anything. So it just Depends on whether he would or wouldn't do it, or did or didn't do it, kind of thing. But in terms of the quantum physics, there we have mentioned some assumptions. So that this notion about the real and imaginary thing, that's something that I think is nonsense, right? So imaginary time, imaginary
Well,
numbers. So Stephen Hawking,
yeah.
for example, uses this to explain the origin of the universe. He substitutes imaginary numbers into I think it's one of Einstein's equations, one of these equations. So for example, an imaginary number would be the square root of a negative number. That it just doesn't work on
Yeah,
your calculator. But these cosmologists can use it, and that creates imaginary time where the time dimension curves into another dimension of space, or something like that, right? And that's how Stephen Hawking argues there was no beginning of the universe, so to speak. There doesn't come to a singularity point. And that's similar, that's the same concept that Paul Bruney is using. He appeals to imaginary time, and that not these are concepts that only work in the abstract realm. They have no metaphysical reality to them, is what I would argue.
Well, no, they only have metaphysical reality. They have no actual reality. They are ideas.
But
you wonder
but Paul's
whether they're in fact.
assuming there is an ontological realm that corresponds to imaginary space and time.
Yes, yes. I mean, he's at pains quite often to say that imaginary doesn't mean fantastical or just something which only occurs in the human imagination. He means it is something which is mathematically definable, whether or not it actually exists in real life, if you see what I mean. So it has a reality which you can interpret from a mathematical view, but it might not necessarily have any from our point of view. Unless we can come up with some experimental observation, we can't say that it's actually true. But it's not that he's saying I'm just going to make this up out of the air.
It is.
I mean, I often this is something you could explain. What is a minus number? If you've got -4 bananas in your basket, does the basket get heavier? Does it get lighter? What does it mean to have -4? And in real life, you go, well, it doesn't mean anything. It's a useful concept in some circumstances, like, for example, in accounting, -4 bananas might mean that you owe somebody some bananas, so that if somebody else gave you 4 bananas, you could then pay those bananas back and you'd have no bananas. So -4 + 4 = 0. But you can't actually have in your hand -4 bananas. This is so as I was saying, there's a mathematical construct which is useful when we come to using -4 bananas, but you have to use it in the right circumstances. You can't go and get a basket of them.
All right. And the last thing, so I understand I'm in the minority in terms of scientists and physicists, but
No, not necessarily. You're saying that you don't believe it, and that's fine. A physicist is saying that we don't have enough information to believe it or not, which is
and like I said, I'm a philosopher, so I reject these things on a metaphysical reasons or logical reasons, I would say. But here's what I wanted to say in terms of he mentions that I was looking for it, where he talks about the past, present, and future. Only imaginary past, present, and future states exist. So he says the past, present, and future exist, at least in the imaginary realm. I'm not sure about the real realm, but I just wanted to ask you. So I adopt an A theory of time, a tensed theory of time. It's known as presentism. So it says, ontologically speaking, only the present exists. The past and present don't exist in any ontological sense. Now, and for that reason, I'm just wondering, number one, if presentism is true, would that falsify Paul Bruney's view? Because he said he has to assume that there is a past, present, and future that exists ontologically. I'm not sure if that's just in the imaginary realm or also in the real realm, and whether that makes a difference or not. And the second question is for you. I know you're a scientist, and the majority of scientists adopt a B theory of time, which says, yeah, the past, present, and future do all exist in a space-time continuum, a four-dimensional space-time continuum. So on that front, Paul would be in line with
Yes.
modern physics. So what's your take on
Well, it depends what you mean by physicists thinking that they do exist. I don't understand. I can't find Bruni's idea, but this is a philosophical rather than a scientific thing. We can say that if a car is here and it's traveling at that direction at such and such a speed, then it was there. But that doesn't mean that we still think that in some mysterious world it is still there. We simply we can say a lot about the past, and we can say how the present has been achieved from the past by using the space-time continuum. And we can do interesting things like saying that as we look at enormous distances, we can look back into the past. So if we say that the nearest star is 4.5 light years away, we're not saying that we're looking, as it were, at the star at the present time. The star, we're looking into the past. We're simply seeing now what was happening 4.5 years ago. That's not the same as saying that the past actually exists as a real thing.
Great. So you are the same as me. You would adopt an A theory of time. You are a presentist. Now, the majority of scientists, actually, everyone attributes it to Albert Einstein. It wasn't him. He came in with a scientist named Minkowski. So the space-time interpretation is that actually, yeah, if you draw that line of the cars, the past, present, and future all exist. They actually exist in a space-time continuum. And if you built a bridge through a wormhole, you could actually travel. That car from 5 minutes ago exists. If you had a wormhole, maybe you could travel there, kind of thing, or you could travel into the future.
Yeah.
And that is what Paul is. I think he's assuming. But the only thing that I was asking you about it is physicists like Albert Einstein, Stephen Hawking, all these guys, they assume it exists in reality. But he talks about.
I don't think they did. No.
He's talking about it in.
I don't.
Yeah. Do you know if it's
just? No, I don't think.
Go ahead.
I don't think any of those physicists that the past was actually happening at all.
They do. I can quote them. It's known as the B theory of time. Brian Greene, for example, has an entire book on the fabric of time where he. You know what? Let me find a. You want me to find a video on it if you're interested? But
I would be interested because that's not my understanding of their understanding. If you see what I mean.
Oops. Yeah, no problem. I'm just looking for A theory versus.
Yeah, me too.
Quick little video explaining it.
Oh, if you've got a video, that's even better.
Yep, I'm looking for one with helpful visuals, though. If it's possible. Nothing. Okay, I'll just play this. Relate to the cosmos. Theory of time. Okay, yeah, this was all right. So let me share my screen. So this is Closer to Truth. This is an amazing series. It's kind of old. It's 20 years old now, but this is Dr. William Lane Craig, who spent 13
Yeah.
years researching the nature of time, but here he is explaining the difference.
We've all wondered about it. But when you think about time and then you think about God, then the two together really cause complexity.
Yes.
How do you deal with God and time?
I remember one philosopher who said that if the philosophical importance of a topic can be judged by the amount of nonsense written about it, then the concept of time comes somewhat ahead of the concept of space and somewhat behind the concept of God.
Right.
And you put God and time together, you have a subject that
Volatile.
is truly baffling and mind-expanding, one of the deepest. I spent 13 years working on this topic as my major research interest, and it's an inexhaustible study.
All right, 13 years worth. Tell me what you learned.
Well, I think we need to talk about the nature of time most fundamentally. I think that this is the question. And philosophers have distinguished two radically different concepts of time that will profoundly affect how you view reality and I think how you view God's relationship to time.
Okay, what are they?
One view of time is what we might call a dynamic theory of time, or a tensed theory of time. And what it says is that the moments of time are ordered by past, present, and future, and that these are real and objective aspects of reality. The past is gone. It no longer exists. The present is real. The future has not yet come to be and is not real. And so the future is not sort of out there ahead of us down the line waiting for us to arrive. The future is pure potentiality. Only the present is real. And so things in time come to be and pass away. There is real, objective, temporal becoming in the world as things come into existence and then pass out of existence. That's the dynamic process or tensed theory of time.
Tensed meaning that there are verbs which have past tenses and present tenses and future tense.
Yes, and that those tenses express objective features of reality. That's the key.
Now, sometimes you call this the A theory.
That's right. That comes from the British idealist J.M.E. McTaggart, who distinguished these two theories, I think, first of all among thinkers, and called one the A theory and the B theory. Not too descriptive, but a convenient label.
The A is the dynamic one.
That's
the
right.
one that I would say is the common perception.
I think it is the perception of the common man. It's the common sense view.
It's a little hard to discern what is the present because we're moving through the present. I don't know how long the present lasts.
That's right.
Theory A, past doesn't exist, future is a potentiality. Now, what's the B theory?
The B theory, or the static theory, or the tenseless theory of time, says that the difference between past, present, and future is just an illusion of human consciousness. That in fact, all moments of time are equally real and existent. The future is as real as the present, is as real as the past. So for the people in 1868 is real, and we are in the future. For the people in 2050, we are in the past, and the present for them is real. But all of those are just subjective standpoints of those observers. In fact, if you could stand back and see things from a sort of God's eye point of view, all moments in time are equally real, and temporal becoming is just a subjective psychological feature of human consciousness, not a real feature of the world.
So that explains. I wish I had a helpful visual there, but
no, that's very helpful and explains it explains quite a lot. And while you were doing that, I was also having a look at Einstein's view of time and Hawking's from that point of view, and the whole concept of the space-time continuum. And the problem, I think, is that I don't think either Einstein or Hawking thought that if you drop a cup on the floor and it breaks, that you could go back, or that the situation in which the cup hadn't broken actually exists. It still exists. I think because they weren't thinking about the small scale. What they're thinking of, and sort of follow this along, is it turned in cosmological terms, and they're saying that from our point of view, and this is what I was saying earlier, we can see things in other in things which are a long way away, exactly as they were that many years ago, and those people can see us exactly as they were that many years ago. So if you can imagine a planet here, I'm going to put it a bit lower here, and a series of stars like that, observing this planet, they are observing it in their real time as it was perhaps 400 or 1,000, or for all I know, 10 million years ago. And if it were possible for somebody, maybe God, to hop around between these places, you would be able to see in real time actually happening things that happened in the past. And I think that's the essence of it. Now, that being true, you could sort of, I don't think either of them thought of anything happening in the future. I think I don't know. Did William Lane Cane mention McTaggart? But this is all about observing things that have happened before from a long way away. And the thing is, you might say, yes, but in that case, how could people say, this is just a long way away, it's not real? But on the other hand, this person here, you can all observe each other, and with the points dotted about, it all becomes you can see, everyone can see everyone else at different periods of history. So in that sense, the past, from an observational sense, and over distance, over space-time, that's why space-time is this huge dimension, then from any particular point, a point in the past is real. But that doesn't mean that it's, from my point of view, yesterday was real. And I don't think Einstein or Hawking thought it was. Does that make any sense?
So it does.
Neither of them projected into the future.
No. So in terms of the starlight thing, you're totally right. That is an A theory of time, or it's consistent with an A theory or a B theory, right? What we're observing here in what we would call the present, regardless of which theory of time you are, what we're observing empirical evidence that exists here in the present, the starlight as it existed 4 million years ago, and it's here now before our eyeballs in the present, kind of thing. And so in that sense, we have evidence of what the planet looked like 4 million years ago here in the present. It's a residual, but we're not seeing the planet as it existed 4 million. We're not the planet doesn't look like that today in the present. But that's a separate issue.
Yeah.
Einstein and Hawking did support, it's called eternalism, or the B theory of time. So with the special theory of relativity, for example, this is considered scientific proof for the B theory of time that says the past, present, and future all exist equally. So that planet 4 million years ago doesn't just exist here in the present through the light we're seeing in our eyes. It also actually exists. If you found a way to travel there through a wormhole, you could travel back in time or into the future or something like that. If there was a way we could do that kind of thing. And special relativity is said to be proof of that. It's not. Obviously, I'm an atheist, but basically with relativity, Einstein in 1908 changed his mind to believing from the A theory to the B theory of time based on a Minkowski interpretation of the special theory of relativity. And I think I have a clip.
I found I found in Einstein a letter here, a letter of condolence, explaining that the flow of time is not fundamental. And he does say, for us physicists, the distinction between past, present, and future is only a stubbornly persistent illusion.
So that's the B theory, right? He's saying it's just a psychological feature, but temporal becoming for me and you, we would say no, it's real. The past doesn't exist. It's gone, kind of ontologically. Whereas Einstein is saying no, it's still there. We just think it's gone, but that's a psychological illusion on our part.
Yes,
yeah, if you want, I can
don't.
play another.
Yeah.
Here's another clip where he actually asked William Lane Craig about relativity, if you're seeing that.
Yeah, I can see the video.
Okay, so
Einstein's relativity theory's proven that eternalism or B theory of time is true?
This is a popular misconception that is unfortunately very widespread. And I think it comes due to the textbook presentation of relativity theory in terms of a four-dimensional space-time geometry. But that is simply a way of presenting the theory diagrammatically. You use a four-dimensional geometry to present the theory, but it shouldn't be construed as a serious piece of metaphysics. Historically, there have been at least three main interpretations of special relativity. The first was Einstein's original 1905 paper, where he represented special relativity in terms of an A theory of time with three-dimensional objects enduring through time. In 1908, the physicist Hermann Minkowski showed that the theory could be much more simply presented in terms of this four-dimensional geometrical presentation. And so he proposed this space-time interpretation of special relativity, which Einstein then adopted and became then the standard textbook way of explaining the theory to students. But in addition to this, there was H.A. Lorentz's view, which was that relativity is a feature of the subjective perspective of the various finite observers in spacetime who are in motion relative to a fundamental reference frame. And since uniform motion affects the speed of one's clocks, that affects how different observers in motion will measure the amount of time elapsed. So on Lorentz's view, there is absolute time, absolute length, absolute motion, but these are simply undetectable by us through our measuring instruments.
So yeah, I just wanted to show this. So that Einstein, as well as the majority of physicists today, who you and I agree would be wrong, think they take this eternalism or a B theory understanding of relativity theory, where there is no absolute fundamentals or absolute reference frame and stuff like that. It's all relative, including time and stuff. So it's just a psychological feature that we think now is the present, but really the year 2050 exists and the year 1950 exists. They're just as real on the space-time continuum as the year 2025. Now I think you and I would both agree that that's nonsense. I think that's nonsense and not true.
Well, I think I certainly agree that that's nonsense. But do you know, I think that quote of Einstein needs to be taken in context. He wrote it in a letter to a person who I think had just lost his wife. His Michel Angelo Besso had just died recently. who was a lifelong friend of Einstein's, and it was 4 weeks before Einstein himself died. And I don't think that any of his published physics actually supports what he said, funnily enough.
Right. You're right.
But
yeah.
he says, yeah, for us believing physicists, the separation between past, present, and future is an illusion. But what he said just before that is quite significant, because he begins by saying something like, our friend has just gone ahead of us, and we might be able to catch up, is the idea. But I don't think, as a physicist, he really thought that. He might have thought that as a human being, but he didn't. He never demonstrated that in his writings. There are lots of different translations of it, but that seems to be mostly it. But it's the bit before. With his departure from this strange world, he has now gone a little ahead of me. This is of no significance. For us believing physicists, the separation between past, present, and future has only the meaning of an illusion, albeit a tenacious one. So it's as though Einstein was hoping that after he died, he'd be able to catch up. I think there, Einstein he may have just been being nice, but I think he was groping towards his own version of heaven in a physical way, rather than actually defining it in a scientific way.
All right, cool. Well,
anyway, there may be people who really do think that the future actually exists and is totally fixed. To which you can only say, well, this is sort of Schrodinger's cat again. We won't know until we get there. And at the moment, it doesn't matter whether it's fixed or not, does it? I mean, who knows? Who cares?
Yeah. All right. Fair enough. Well, that's it that I have in terms of I think we covered everything in terms of my notes about Paul Bruney's theory. Is there anything else? Anything else? Oh, well, reverse causation. I don't think Paul Bruney. I was thinking about reverse causation. Like causation traveling back in time, but Paul Bruney doesn't depend on that at all. The phase inversion has nothing to do with that.
Well, no. There are very interesting ways of seeing the flow of space and time, and some of them are not are not dependent on cause preceding effect, and some of them are, but they're very much thought experiments rather than justified by observation at the moment. I don't think I could say much more than that, really.
And it's not relevant to Paul's hypothesis anyways, so I guess we can.
No. Okay. I mean, in simple terms, you might say that I went out this morning, and of course it is your morning or still, but afternoon for me. But this morning I went and bought a birthday card. Now, the reason I bought that birthday card was that it is my sister's birthday in 2 weeks' time. So the future has inspired it was the direct cause of my buying that card, was something which hasn't yet happened. How do you account for that?
I think it was due to the influences that exist on you in the future, including your desires for a future state, to bring about a future state, which exists in the present. So that's how I would. All right, cool. And just before we wrap up, is there anything else about Paul's hypothesis that I didn't ask about or that we missed? Is there anything else we covered it?
No. I think we've looked at it as best we can within the context that we have, and I hope Paul listens to this and is able to clarify the bits that we've said are confusing to us.
Yeah. And Paul, if you want to, either reschedule or something like that and come on and just answer the show or something, or if you're it'll be up to Hugh. I don't know if he'd want to reschedule and stuff, or if you just want to write a response, I'll post it up in the comments and on my blog for people. So either way, you can respond to this show, and I'll send him the link. So yeah, thank you so much, Hugh, for showing up, and thank you to Paul for
past the time. Really good. Yep.
Absolutely. Yeah. And thank you to Paul. I will be posting on my blog for the show in the YouTube video description. Paul has his original paper, but he also wrote an updated paper and sent it to me and Hugh for this show. So I'm going to have the link to that. And I will also have Scott Hill's paper on the resurrection for you guys, along with some other sources. But other than that, coming up in future, so next week, Eucharistic Miracles. Kevin Nontradikath has found a debate partner, a friend of Franco Serafini. Franco, unfortunately, flaked out on doing the debate. I don't know why people are doing that, agreeing to do the show and then not showing up. I don't know what's going on with that, but Franco did flake out, but he found somebody else to debate. So I'm going to be posting up that debate and then doing a debate review in the following week. But for Shroud fans, I will be having Stirp scientist Rudy Ditchlittle. I don't know how to say the last name, but Rudy Ditchlittle will be coming on in July to share his experience. He was best friends with John Jackson and Eric Jumper, and he has a whole lot of stories regarding his friendship with these Stirp scientists before, during, and after Stirp. So that'll be sometime in July in terms of the Shroud. The other and last update is the debate with beloved Hugh Farey right here on Hugh's image forming hypothesis. So far I've done about four shows on that topic, but we haven't done a debate proper, apart from the first one we did with Teddy and Hugh. And unfortunately, Rudy doesn't want to do the debate on Hugh's image forming hypothesis. So that means it is up to me. Hugh will have to settle for me as his debate partner. But I will need some time to prepare, but maybe sometime in August after the conference, we'll set up a debate and we will discuss your theory, pro and con, both sides. Sound good?
Yeah. Very good.
Awesome. All right, guys. Well, take care and have a great week, everybody.